is Nicolau Saldanha, and he'll talk about examples of dynamics of eigenvalue computation.
So thank you. Thanks for the organizers for the opportunity to speak here. This is joint work with Ricardo Leite from Espírito Santo and Carlos, who is right here, my colleague in PUC. So, well, what we're going to be talking about is matrices, especially tridiagonal symmetric matrices. A matrix is tridiagonal if it has diagonal entries and off-diagonal entries immediately below and above the diagonal, but nothing else. The rest is zero. And it's a major problem in applications to, given such a matrix, to compute its spectrum. Why would you care about tridiagonal matrices? For two reasons. Sometimes spontaneously your application leads to a tridiagonal matrix because you have objects which interact with neighbors. And also another reason is it's very easy, given a full matrix, to tridiagonalize it. So if you know how to compute spectra of tridiagonal matrices, you basically know how to compute the spectrum of any matrix. Now, a matrix is unreduced if its off-diagonal entries are non-zero. Maybe let's make a drawing here of a matrix. So tridiagonal means it looks like that. Unreduced means these entries are non-zero. So reduced, in other words, means that your matrix reduces, as the name suggests, to a direct sum of two smaller matrices. So if you're interested in computing eigenvalues, if you see something reduced, what do? You immediately decompose it into unreduced blocks, and you proceed from there. So it's smaller matrices should be an easier problem. And Jacobi matrix is a matrix such that the off-diagonal entries are positive. Now, if you change the signs here, so say here, if you have a negative sign, if you just change these signs here and make them both positive, you just conjugate it by a signed diagonal matrix, so the eigenvalues do not change. So you might just as well work with Jacobi matrices. But, well, as in many cases, it's not clear whether that's really the best thing to do, because maybe the presence of reduced matrices and even of diagonal matrices, maybe it will help us. Well, maybe it depends on what exactly you're going to do. We shall see this kind of thing during the talk. Now, this process, which, given a tridiagonal matrix, obtains another tridiagonal matrix with the same spectrum, which is called the general QR iteration. So you start with a matrix T0 and a continuous function f. Now let's assume, for now, that f is non-zero in the eigenvalues. Okay, we're going to drop that a nice condition in a minute. But then you take f of t0. Now f of t0 here, of course, means you it's functions of matrix, like you diagonalize your matrix and apply it to the diagonal. So you compute f of t0, factor it as a product QR, Q orthogonal and R upper triangular, and you do that. You conjugate your matrix T0 by either Q or R. Now, since f of T0 and the product QR commute, if you write T0 QR and equal QR T0, you deduce that both conjugations give you the exact same thing. That's what we call capital F of T0. And from the first formula means this, the formula with the Q's. From the formula with the Q's, you started with a symmetric matrix, you conjugated it by an orthogonal matrix, so of course it's symmetric. From the second expression, this one, with the R's, this. From the second expression, you take a tridiagonal matrix, you conjugate it by an upper triangular matrix, so of course it's upper Hessenberg. So you put these two facts together, you realize that f of T0, or T1, is also tridiagonal. So calligraphic T stands for the matrix is tridiagonal, symmetric. And its conjugate to T0 has the same spectrum. Okay. So many algorithms to compute spectra of matrices, they're based on the idea that you're going to iterate this process. Okay, you're going to iterate this process and you're going to approach a diagonal, or at least a reduced matrix. If you approach a reduced matrix, you split it into blocks and you get much easier problems. Now, even if you do the most classical QR iteration, which is for f of x equal x, meaning you factor the matrix itself as QR, even if you do that, if you iterate, then generically at least you're tending to a diagonal matrix. So you could say, well, that's a very good algorithm. Well, it's, if you are a pure mathematician, you may say it's a good algorithm, but from the applied point of view, you have reasons to complain. It's not fast enough. It's only linear. You are approaching a diagonal matrix, but it's not as fast as you would want it to be. So there is one very minor variation, which is instead of taking f of x equal x, you take f of x equal x minus a shift. So if you do that, it's still very easy to compute the matrix minus S, right? You don't want a complicated function f there, or else it's going to be hard to compute f of t. But just making a shift is something very easy. So you do a shift and you apply that. Now, how exactly is that going to help? In order to see how it's going to help, I invite you to consider this degenerate case, the case which we at first didn't consider, which is what happens if the shift equals one of the eigenvalues. So what happens is T0 minus lambda I is not invertible, but you can still factor it. You can still factor it as a product QR, Q orthogonal or upper triangular. Well, upper triangular here does not exclude that, right? The 0 at the corner. You're still a triangle, even if it's 0 at the corner. So the formula with R inverse doesn't make much sense if R is not invertible, but that's okay. We have the formula with orthogonal matrix that still does make perfect sense. And that matrix is no longer unreduced. What happens is you isolate at the bottom the eigenvalue, which is the shift itself. But you can say, well, that's what's the point? I mean, if you know the shift, if you know one eigenvalue, you just discovered the eigenvalue which you already knew. No, the point, of course, is if you have a reasonable guess for an eigenvalue, then you use that as a shift. And then you are approximately, in this situation, then the entry t n minus 1n, it's not going to be exactly 0, but it's going to be very small. And then you repeat the process, and it's going to get as small as you need. So the idea is take as close to an eigenvalue of t. Okay, so that's a problem. Now, what we're going to discuss is what's a mathematical structure, or rather the several mathematical structures which are behind this problem. But before, or maybe as part of that, one very nice theoretic observation here is that the step is interpolated by an explicit differential equation, so todo flow. If you consider that equation, where pi a means projective over antisymmetric matrices, okay? Because you need an antisymmetrical skew matrix there, so that when you take the bracket, you get symmetric. And it turns out that the todo flow interpolates these generalized QR steps. So that's nice. And notice also that, well, it's related to this, that all these generalized QR steps and all these vector fields, or the flows rather, they all commute. So we should consider them as a family. They are all acting simultaneously there. So, question is, what's the correct structure for this problem? How should we consider this? Now, one point of view is, if you look at a set of Jacobi matrices with a prescribed trace, for instance, trace equals 0, then that's a coadjoint orbit of an action, and therefore it has a symplectic structure, and the flows and the iterations and all the objects we constructed, they respect that symplectic structure. So the maps F are commuting symplectomorphisms, and the flows, they also respect symplectic structure. So if you consider the orbit not under one instance of F, but all such maps and all such flows, the orbit of a matrix T0 is a set of all Jacobi matrices with that given spectrum, okay? So if you have that much structure, you can see that, well, or you can abstractly see that a set of all Jacobi matrices should be just Rn, and your maps should be translations, and your vector fields should be constant vectors over with a certain change of variables. So that's a torus, except that it's open, right? It's Rn minus 1. And norming constant introduced by Moser, they are the first coordinates of the normalized eigenvectors. They are the, well, there's a key ingredient, and not exactly the diffeomorphism promised there, but they are the key ingredients towards building explicitly that diffeomorphism. Explicitly, of course, from a theoretical point of view, assuming you know everything, right? It's not explicit in the sense that it's an easy computation, which you do. So Moser studied, with the help of norming constant, he studied these vector fields and these iterations, and he showed that what we saw for the plain vanilla QR iteration, it happens generically for these generalized QR iterations, and it also happens for the flows. You're almost always standing to a diagonal matrix. Now, the diagonal matrix is outside that space, right? It's not Jacobi, which, of course, it couldn't be there, and you couldn't have everybody tending to a diagonal matrix and at the same time be volume preserving. Something is wrong here. And what happens is a diagonal matrix is outside that space. Okay, so it's nice to have a structure on the set of Jacobi matrices, but from another point of view, if you want to study the asymptotics of the iteration, and you want to ask, for instance, how fast am I converging to a diagonal matrix? How fast am I converging to an unreduced matrix? Then you should have a phase space which includes the limit points. So how can you do that? Well, the most immediate idea probably is to consider the set of Jacobi matrices with prescribed spectrum lambda and look at its closure as a set of matrices. So we are therefore including not just Jacobi matrices, but also reduced matrices such that the off-diagonal entries are non-negative. Okay, so that includes the diagonals, and it turns out that J lambda bar is a manifold with corners. Okay, and it's homeomorphic to a certain specific polytope called the permutohedron, which you get by permuting numbers. In this case, you permute eigenvalues. You take the convex hull, that's a convex polytope, and it's homeomorphic to that. Bloch, Flaschka, Hartue, they give an explicit map, and Leite, our co-author, gave different proof of the same result. And here in invisible ink, can you there's supposed to be a curve here. There, you. É para ter um hexágono ali. Por que ele está invisível? Aqui não dá para escurecer, não? Apaga aqui um instante. Bom, I'll draw because it's drawn here as a hexagon, but you cannot see it because there's too much light. So here you should see this, which is a permutohedron with the 6 vertices shown there. And here you have the set of tridiagonal, symmetric tridiagonal matrices with a prescribed spectrum with non-negative off-diagonal matrices. It's a surface in some high-dimensional space. I draw it curved like that to suggest what it more or less looks like. We're going to see some pictures, I hope at least, but the other ones are going to be visible next. So now if you're going to approach the boundary, maybe it's nice to have the boundary not at a special boundary point, but so to speak, to resolve the singularity. Okay, to have the boundary be an ordinary point. Okay, so one way to do that is to consider this manifold. It's a manifold of matrices with the prescribed spectrum. Now you're free to be reduced. You're allowed to put negative off diagonal entries. So, well, that you can see, fortunately. That manifold is obtained by gluing permutohedra, and it's, well, here in n equals 3, it's a bitorus. Now let me explain very briefly how this bitorus is drawn. What you have is n equals 3, so we're talking about 3 by 3 matrices. You have 5 numbers. Well, actually not 5, because the trace is constant, so you have a surface in R4. Well, actually there's another thing which is constant, which is the sum of the squares of the entries, because that's the sum of the squares of the eigenvalues, which is also constant. So you really have a surface in S3. So you take S3 and project it stereographically to R3, and you ask Maple to plot it, and you get that fancy armchair there. We'll come back to this picture to talk more about the grid. Okay. Because in order to draw that, well, you don't just give Maple a verbal explanation like that. You have to actually parameterize the surface somehow, or else it's not going to know what you're talking about. So there is this nice atlas of the manifold T lambda, which is, these are the bidiagonal matrices. And how is it defined? So you take a matrix and a permutation, because we need a family of charts, of course, right? You're not going to parameterize a bitorus with 1 chart. You're going to parameterize a bitorus with 6 charts, 1 for each permutation. And now you factor your matrix Q pi as LU, L lower, U upper, and you write, well, you can choose Q so that U has positive diagonal, just to make things more uniform. And then you consider that. You take, well, this matrix B, which is sort of in between T and lambda pi, and that's a bidiagonal matrix. It's bidiagonal. On the diagonal itself, you get the eigenvalues, and below the diagonal, you get numbers, let's call them betas, which define a chart. It's a chart and an open dense set. So let's go back here. The grid there is obtained by the 6 charts. Okay, you can see the 6 charts meet here. You see the star there? I can't go that high. But here is a star. That's where the 6 grids meet. And the 6 grids, they are centered on the diagonal matrices. Let's not, instead of jumping, well, this one is visible, lighter than ideal, but still visible. That's what the set UPLA is a domain of the parameterization here. It's a set of matrices for which this algebra is possible, okay? Because there's no guarantee that Q pi admits an LU factorization, but it usually does. It does in an open dense set. So that set looks like a polytope. That polytope is obtained by gluing 2 to the n minus 1 permutohedra around a diagonal matrix. And if you glue the edges of that polygon, you obtain the manifold T lambda. Okay, so that's a very explicit description of T lambda. But you may think, well, we're going off track here. I mean, that was not the aim was not to discuss the topology of the manifold T lambda. The aim was to study the maps capital F and to the flows maybe. So it's nice to have an atlas, but what good is it if I cannot translate F into these coordinates? But that's the trick. You can actually. It can, and it becomes incredibly simple. You see, the map capital F in this bidiagonal coordinate, it becomes a diagonal matrix. Yeah? You multiply each bidiagonal coordinate by a fixed number. Okay? Which makes sense, right? If these numbers are all smaller than 1, then you're doing this. Ooh, you're contracting towards the origin, consistent with the fact that these iterations should converge to diagonal matrix. Now, if we consider QR with a shift, well, more general actually, but let's stick with a situation where we're doing QR with a shift. You might say, well, there's this slightly annoying fact that we have these absolute values. Well, what's wrong with absolute values? It's wrong that it's not smooth, it's not analytic. Okay? You have that thing there. So that's bad. But that can be solved. Yeah, we can get rid of it just by changing a sign at the end. That sign of the end, it does nothing too important. It just changes this sign here. Doesn't change the spectrum. And it has this nice effect that now we have a smooth, even an analytic family of maps. Okay? Now for S equal lambda pi n here, the map is degenerate, right? The last coordinate is being taken to 0. Now, what does that mean in terms of matrices? That's the translation into bidiagonal coordinates of the fact about which we talked 3 slides ago. That if you do QR with shift, and your shift is exactly an eigenvalue, you reduce your matrix. Reducing your matrix is having that last coordinate equal to 0. Yeah. but the nice thing is we can take care of all these iterations fs star simultaneously for all s in an interval, which I'll not make precise what it is, an interval near lambda pi n. And they all simultaneously work together. It's analytic, everything works. So, well, that's nice. But let's go back to the point of view of numerical analysis. The point of view of numerical analysis is we have these matrices. We want to find a spectra. In order to find the spectra, we do QR iteration with shift. And we choose a shift as a guess of one of the eigenvalues. So a shift strategy means you have a map which for any matrix gives you a shift, okay? And the condition that you're trying to guess an eigenvalue means, well, if your eigenvalue is almost obvious there at the center, your guess should be approximately that. Yeah? You're not going to try and guess something completely different from what's obvious. I'm not requiring sigma to be continuous, by the way. I'm just requiring that limit to hold. So for such a shift strategy, we have this map. Now that map is not nearly as nice as f sub s, which means given a matrix, find a shift, and apply QR with that shift. Okay, and that's what's written here is actually not 100% correct, because if I shouldn't write here T lambda, because if sigma happens to guess an eigenvalue precisely, then it's not defined everywhere. It's only defined on the regions near the reduced matrices of the correct order. But, well, morally it's correct, let's say. So let's see exactly where it's correct. We define these deflation manifolds. Deflation is this process of going from unreduced to reduced. You get some entry which is 0. You said, oops, we just split a big matrix into small ones. That's deflation. And d lambda 0 I means we deflated there at the bottom, not at the center. It's by the way, it seems much easier to deflate at the corner than at the middle. It's a good question why. But we want to deflate our matrix like that. Okay, we want this entry here to become 0 and some eigenvalue to get cornered there. So d lambda 0 I means you won. You cornered an eigenvalue. And d lambda epsilon, these are neighborhoods of these submanifolds. It means, well, you haven't literally cornered your eigenvalue, but you are in the process of doing it. You are already approaching it. And that condition at the top says that these neighborhoods, they are invariant. And the fs, well, there should be a star here, or there could be, it would be preferable to have a star here. And therefore also under f sigma. So in order to study fs, we consider the family of much nicer maps fs from the neighborhood to the neighborhood. Maybe you want to put a star here, where the little hand is. and then you have these maps. These are not volume preserving at all, by the way. You are volume preserving when you restrict yourself to Jacobi matrices, but if you are talking about unreduced matrices, if you go back to the symplectic structure, you would have an infinite volume here. So, well, it's not a volume on that manifold with boundary there. It's a neighborhood. And actually, for s equal lambda I, you're taking a manifold of dimension n minus 1 to a manifold of dimension n minus 2. So that looks definitely not volume preserving. So if we want to study the dynamics of one of these algorithms, and so what an algorithm is a shift strategy, okay? For instance, there is Rayleigh's shift strategy, which says take as your shift the corner entry. There is Wilkinson's shift strategy, which says take the bottom 2 by 2 block, compute its eigenvalues, choose one, that's your shift. There are many algorithms like that, which are variations of QR with shift. If we want to study the dynamics of that, we want to study the dynamics of this here, of these maps going from a manifold to a manifold. Now, in order to understand a family of maps, we have to make a certain classification here, because the presence of an arithmetic progression in the spectrum is going to make the dynamic very different, okay? Because, well, so here is a classification. A matrix is strong AP if it has 3 consecutive eigenvalues in arithmetic progression. Something, of course, of measure 0, right? It's not. It's weak AP if you have 3 eigenvalues in arithmetic progression, but they're not consecutive, okay? So it's still something exceptional. And it's AP3 otherwise, so that's the generic situation is AP3. It means you don't have an arithmetic progression in the spectrum. ASP stands for arithmetic progression, obviously. Right? So if lambda is AP3, then these maps, this family of maps, they all have finitely many fixed points. And the fixed points are the same for all of them. These are the diagonal matrices. Now, if that doesn't, if you're not AP3, then it's not true anymore. Then you have many fixed points. If, for instance, if you have these 3 eigenvalues in the arithmetic progression and you take S exactly equal to this eigenvalue here, then you have not just the diagonal matrices which are fixed, but you have other matrices, like this matrix here. It's fixed under the standard QR iteration. And now that we know we have only these finitely many fixed points, it would be nice to understand which fixed points attract the neighbors, which are saddles, and so on. So a good step in that direction is to produce a height function. So a height function means something which always goes up by your iteration. It's like the entropy, something that becomes larger. So let M be a diagonal matrix with strictly decreasing diagonal entries. There's a theorem by these four authors, deste, Tomei, Watkins, which says that if f is positive and strictly increasing, then the trace of m times f of t is larger than or equal to the trace of mt. So this smells like a height function, but that's not precisely what we need. What we need is an application of this theorem. Okay. And if you apply it to this situation, you get that function is a height function. And capital H is a height function. I mean, it always goes up, except for diagonal matrices. For diagonal matrices, it stays constant. Of course, it stays constant because the matrix itself stays constant, but otherwise it goes up. Now, this is going to help us understand the dynamics. And now, from this point on, we illustrate these ideas with an example, with the example of Wilkinson's shift. Wilkinson's shift is one of the favorite shifts from numerical analysts. And one of the reasons it's popular, well, there are many reasons it's popular. It's popular because it's easy to use, to implement. It always works, and it works fast. Okay, so let's discuss these virtues of this method in somewhat more detail. So, okay, you take the 2×2 principal minor of t, let omega of t, so we consider this block here. You compute its eigenvalues. It's a 2×2 matrix. It's easy to compute eigenvalues. And you check which is closer to this. And you choose that as a shift. Notice that omega is discontinuous because exactly who is closest is something which changes when the two are at exactly the same distance, which is equivalent to that condition. And now you define Wilkinson's shift as, well, that. And we want to study that map. Ooh. Yeah. So, some known facts here. Given deflation, given lambda, deflation happens uniformly. I mean, you have a given number of steps, you always converge. And that's thanks to the discontinuities. What does this mean? Deflation is going to take you either here, or here, or here. Now, if you have a continuous map, you are in trouble. Something is going to get stuck in the middle, right? Now, Wilkinson solves that problem by cutting this in some way. You have discontinuities here in some way. And the annoying thing is sometimes the discontinuities, they approach the limiting set. Now, big question here, what is the rate of convergence? Ooh. It's at least quadratic. That's a well-known fact. Is it cubic? That's a question which has been asked, and in a sense, that's a question which we're trying to answer here. Is it cubic? When is it cubic? Always, almost always. Well, let's discuss the situation of AP3 matrices. For AP3 matrices, quadratic convergence happens uniformly, as we saw, and cubic convergence almost does. I mean, we are going to have cubic convergence, but not uniformly in the most natural sense you would expect. That you say you have a constant c such that this error is c times the cube of the error of the previous step. That doesn't work. That doesn't work because of these bad points here. So dangerous regions is when you approach a discontinuity. A discontinuity isn't so dangerous by the fact of being discontinuous, but by the fact of being not smooth. If you're not smooth, you can't control the expansion there to have cubic convergence. So what happens is this. It's uniform, not in the sense that you have the same constant for everybody, but in the sense that there is a constant and there is a bound on the number of bad steps, the number of steps that violate the cubic convergence estimate. And it's written in this complicated way, it's not just, the stronger thing is false, okay? You can construct examples where you violate this, and you violate it arbitrarily late in life, okay? So you cannot guarantee uniformity in a more natural sense. Now, if the spectrum is strong AP, how many minutes do I have? 10 more minutes. Okay. If the spectrum is strong AP, which means I have 3 consecutive eigenvalues in arithmetic progression, then cubic convergence is really going to fail. Okay, so this example, this tiny example here, 3 by 3, is something we studied in detail. And in the neighborhood of this matrix, this is a very nasty matrix for Wilkinson's iteration. In the neighborhood of this matrix, well, convergence is cubic in an open dense set. Cubic convergence is a rule, okay, it's what you would expect. But there does exist a set of codimension 1 where you have strictly quadratic convergence. The closed set it's a Cantor-like set. It has Hausdorff dimension 1. Let me show the picture first and then come back. Well, maybe you don't see a Cantor, well, I'm sure actually you don't see a Cantor-like set here. You see 4 curves. Maybe if your eyes are very good, you can see that here it's like a hair which is slightly splitting at the tip. Okay. What happens is that this is a Cantor set, but this is a Cantor set of Hausdorff dimension. Well, the cross section is a Cantor set of Hausdorff dimension 0. So much thinner than the usual middle third Cantor set. So it's becoming thin, and it's becoming thin very fast. So on this set of curves, if you start here, what happens is Wilkinson's iteration takes you here, and then here, and then here, pa, 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 pa. And you always remain in the dangerous region, and then your convergence is quadratic, not cubic. And coming back here, that's what we conjecture happens in general in the strong AP case. in the strong AP case, I believe you have a picture which looks like that one. You have this Cantor set, and well, sometimes when you deviate from that exact situation, the Cantor set, it begins to disintegrate, and it begins to disintegrate from the bottom, not from the top. But that's conjectural, or maybe I should say work in progress, whatever it things which haven't been thought about as carefully as they should be. So this leaves us an intermediate situation of weak AP. If you are weak AP, then again consider a sequence of iteration by Wilkinson's strategy. And well, if you allow for reduced matrices, then the difference between weak AP and strong AP is moot, because you isolate the 3 eigenvalues in arithmetic progression. You isolate them here at the corner. You put 3 eigenvalues in arithmetic progression here, and the rest there. And then you fell on the situation which we saw in the previous transparencies, the set X, and then you have quadratic convergence. But from the applied point of view, that's sort of an irrelevant observation, because if you're reduced, well, you wouldn't be doing this in the first place. So maybe we should think what happens if you have an unreduced matrix. What happens is, well, you can't have that. Then the convergence is cubic, but there's no uniformity. There's no uniformity in a sense exactly because of the same remark. Because, well, you can't draw that because that's reduced, but you can approach it as much as you want, and therefore you can postpone the moment when the eigenvalues are going to reshuffle themselves. You can postpone it for as long as you want. Just make this entry here very, very, very small. So convergence is strictly cubic. Ooh. But it's not uniform. You can have as many steps as you want with a fixed spectrum, not changing the spectrum. With a given spectrum, you can have as many steps as you want where the cubic estimate fails. Okay. So that's it. These are our preprints and papers. And thank you.
There are questions? If not, let's thank Nicola.
Okay, thank you.